I want to tell you about two reactions of aromatic compounds that don't involve the aromatic ring. One of them is the NBS bromination of alkylbenzenes. As you see from the equation here, this is selected for the benzylic position. Just to get the terminology right, this carbon that is attached directly to the aromatic ring is called a benzylic carbon. And you see that we're replacing the benzylic hydrogen with bromine. Using this reagent we've seen with allylic systems called NBS. Here it is down here in the left-hand corner. Strange looking reagent. The point is, with light, this nitrogen-bromine bond breaks. And two things happen. It forms bromine radicals, very low concentration, and also low concentrations of molecular bromine. So NBS is a source of two reactive reagents that we need for this reaction. Now I've written a compound that has a CH2 group attached to the benzene ring, but it doesn't have to be CH2. There can be an alkyl group there as well. For instance, if there's a methyl group there, there'll be a methyl group in the product. We'll still see bromination at the benzylic position selectively. And in fact, this can be any alkyl group. So let me just replace the CH3 with R. So you know that this is a general reaction. However, it doesn't include all alkylbenzenes. If there are two alkyl groups there, there's no benzylic hydrogen, and this reaction does not occur at the benzylic position. In the event that there are multiple CH2 groups here, we'll see bromination at each of them. Now you might say, no, this is pretty familiar. Didn't we see something like this with alkenes? And in fact, we did. Treatment of an alkene with NBS and light selectively brominates at the allylic position, the CH2 that is attached directly to the alkene. So we see a clear analogy here, but there is a difference. You may recall we said that the allylic radical, that's an intermediate in this reaction, can rearrange. We actually get two bromination products from an alkene like this. When we're talking about alkylbenzenes, bromination gives it a single product, exclusively at the benzylic position. So what accounts for the selectivity? Drawing on your knowledge of radical bromination, the initial step in this reaction makes lots of sense. The single unpaired electron of bromine will pair with one of the electrons of this sigma bond, abstracting a hydrogen and leaving the other electron of this bond on carbon. Now we've made what's known as a benzylic radical. And this guy is especially stable. We can account for this in terms of our resonance theory or MO theory. Let's look at the resonance explanation first, because it's very common. Once this benzylic radical is formed, it's actually resonance stabilized by interacting with the aromatic ring. We can use our arrow pushing to track formation of one resonance structure and another and another. When these guys pair to form the double bond of this resonance structure, it leaves a lone electron on this carbon up on top. This guy can pair with one of these, which leaves a lone electron on this carbon. That lone electron could pair with one of these pi electrons, which leaves a lone electron on this carbon. So you see there are four possible resonance structures for this compound. The initial radical, and three other resonance structures that involve the pi system of the aromatic ring. And you know, one of our axioms is that if resonance structures are possible, they will contribute to extra stability of the system. At the same time, we could look at this benzylic radical as being stabilized through simple interaction of p orbitals, using our MO theory. Now remember, we're trying to account for the reason that a bromine radical would abstract a hydrogen at a benzylic position and not at some other methylene position further away from the ring. We're comparing actually the relative rates of formation of this benzylic radical and some non-benzylic radical. And those rates of formation correspond directly with the stabilities of the radicals themselves. The more stable the radical, the more rapidly it's formed. That's the Hammond postulate. When we look at the MOs of these two systems, we see that the p orbital of this benzylic radical can overlap with the pi system of the ring. And we know that extended overlap is stabilizing, and leads to more stable MOs than if we don't have overlap. So without even drawing the energetics of the MOs involved in this benzylic radical, it's easy to understand that this orbital overlap would lead to a more stable structure. And when a hydrogen is abstracted away from the aromatic ring, that orbital overlap is not possible. This methylene group is intervening. So, resonance theory would tell us that there's no resonance stabilization possible. MO theory would say, hey, those p orbitals don't overlap. They can't lead to especially stable MO energetics. In either case, it's easy to see that the benzylic radical will be more stable and therefore will be formed faster. So, to summarize, when an alkylbenzene is treated with NBS and light, we have low concentration of bromine radicals and low concentrations of bromine, initial abstraction of a hydrogen by a bromine radical makes an especially stable benzylic radical, which reacts with molecular bromine that we can follow with arrow pushing. One electron stays with bromine, the other one makes the new bond together with this radical. So in the second step, we make the product that is selectively brominated at the benzylic position, plus a bromine radical, which can react with another molecule of alkylbenzene in one of the propagation steps of this chain reaction. Selective bromination of alkylbenzenes is a very useful tool in organic synthesis. These bromides can undergo substitution and elimination. The alkenes that are formed can undergo addition and then oxidation. So you can make a host of compounds with functional groups next to the aromatic ring, with the selective bromination at the benzylic position being the key synthetic step.